Hello, my name is Aiden Harbick, and I'm a graduate student at Brigham Young University working with the Center for Bright Beams. I'm currently studying a phenomenon called field enhancement, but before I get into that, I want to provide a little background for my research. The bottom line of it is we would like to improve the performance of superconducting radio frequency cavities, or SRF cavities. These cavities have all sorts of applications, such as large particle accelerator experiments like the Large Hadron Collider, semiconductor engineering, and even certain biomedical applications. The real workhorse of SRF cavities is the superconductor. Superconductors are materials that, when cooled to a low temperature, lose their electrical resistance, and electricity can flow unimpeded. This property in turn allows SRF cavities to achieve the most efficient possible power output. A limitation of superconductors is that they require magnetic fields to be pushed out of the material in order to achieve this superconducting state. And if the magnetic field is too strong to be pushed out, the superconducting properties can be weakened or even lost entirely. When the surface of the material is rough and the field gets pushed out, the magnetic field will be larger or enhanced in certain regions of the material where there may be a bump or something like that. This is called field enhancement. The goal of my research is to conduct numerical simulations of superconductors, which will allow us to understand what effects various surface structures have on field enhancement. In the chart on the top left, you can see an example of surface shapes impacting magnetic field. On the left figure, we apply a magnetic field in the direction of the arrow, and the blue circle you see is a little bit of magnetic field called a vortex entering the material. This will cause a decrease in cavity performance, which is undesirable. In the middle figure, we have added a divot perpendicular to the same field as before, and now there is no vortex able to penetrate the material. We only get a vortex on the right when we increase the magnitude of the magnetic field. One issue with these simulations is that they are not taking into consideration the region just outside of the superconductor, where magnetic field can increase or decrease depending on surface structures. I'm currently working on implementing such a simulation. You can see on the bottom right my first result, where I have a magnetic field on the left with a superconductor outlined in white on the right, and there is a decay of magnetic field into the superconductor, which is what we expect. My next steps are to get this same kind of simulation working for a surface which is not perfectly flat like it is here, and then we should be able to fully investigate what kinds of surfaces are best for SRF cavities, and which are most dangerous. Thank you for your time.